Hi, Miss Ringer here. Today we have a more of a talking head video in the beginning because I might will talk, but we'll get to the point when we can go into the new things that I have been designing and doing. I haven't been working on the contact today because, or that much, because I was trying to figure out basically to be able to communicate between the Arduino and the R32 D1 whatever Vemos whatever. If you don't know, this is the same type of board as the Arduino Uno, but has like a ESP32 based microcontroller, so it is a buffed up hybrid between the Uno, and it is pretty good board in terms of like layout, and has like two 5-volt pins, one 3.3-volt pin, so it's pretty good, as well as like yeah, it has like Wi-Fi on it as well, so it's like fucking cool as shit. So the problem was that I didn't have enough pins on the Arduino Uno to be able to like have the all the GUVA sensors, which are the photosensors for the contact processes catalyst chambers. So the first catalyst chamber before, after, and the third catalyst chamber before and after. So these two, the first one's intake and the last one's output, can basically correlate to the total catalyst, basically the total contact process efficiency, as well as these are for the actual like catalyst beds, so we can see like that they deteriorate or something like that. Basically these have 4 pins. The potmeter has also 2 pins, so for the flow system that will also show. This is the second one. This is to control the bypass. So there is one to control the burner's input and one to control the bypass. With the two we can control the total input of air into the system, thus oxygen, to oxidize the sulfur dioxide into sulfur trioxide and then be able to convert it to sulfuric acid later with the absorption in water, or in later stages with concentrated acid, if we are to be able to produce that. So back to the point. 2 potmeters, 4 GUVA sensors, which is 6 already, and we haven't even started to talk about the pressure sensors. This is 6, which caps out the Arduino completely, and there is going to be 2 more pressure sensors for the for the for the exact same thing, because I have a reader here. This is the potmeter's place, which is basically the gear track turns the flow needle here. Fuck me, how do you say this? The needle is here. It is turned by the motor. We'll put that in, and we'll have like a clip of me assembling it, but I had to like take it apart and like, or not take it apart, but like there are like major refurbishments needed to be done before it can be like used, because as you can see that there is here the teeth has all this plastic inside, which you have to manually cut out with a razor, because this is like PEGI instead of PLA, which is more like brittle and stiff, and there's like stronger material, but you need more effort to pull it out. From the PLA, when it is hot, you can basically like pull it out easily, and you don't need to like use the sharp tool. So this, the needle has the potmeter. It's based back to the point, which has the potmeter to show where the actual valve position is, and with that valve position we can estimate the flow input. But if we know the pressure from the pressure sensor, now the pressure sensors are a bit tricky because you have to set the gain, which, and the sensitivity basically with that, how big of a range you measure the pressure. If you increase the gain, basically you increase the amplification, and with that you increase the sensitivity to error and jitter in the system, which will, if there are like any peaks, it also amplifies that, so that sucks. But now the problem is that I have used like 3D printed parts to make the pieces, like the housing and all these, and probably will update these in the future in the near future, but for now we'll roll with these and replace there are like, I don't know, it's not here, whatever, there are the sensor housings, which is just a straight tube with like a T-joint on it, and or like a little, it's like a T-joint, whatever, and the T-joints like side pin has the pressure sensors. This is like here on the side. I screwed on the other pressure sensors open board, and basically you have the pressure sensor, which is a differential pressure sensor that has two pins. One is before the so like it is like so, fuck me, so it is like so, so it is this, usually this is the before and this is the after. So the before and the after, there is like a pressure drop through the here is the needle valve, because there is like flow restriction happening, and as the flow restricts, there is like, as I said, pressure drop, which we can sense with the differential pressure sensor. The differential pressure sensor is very good, but is very sensitive to pressure losses, and with 3D printed parts they tend to leak, and they like suck in terms of like connecting to. Basically, when you have a small tube, like the diameter of this tube, which is like a inner outer 5, inner like 4 or something like that, or maybe 6 and inner like 4, and you have to imagine like you have to put it on this would be smaller. This is not totally like circular. These are, which are like perpendicular to the build plate, so when you like build the things like this, they tend to be circular. Okay, very well made circle, like despite the fact that it has like debris, but it is like pretty good circle. This on the other hand, which is like or like perpendicular to that is like worse, and you have to like be able to either make the trade to have the T-joints, this is like a similar T-joint, but you have to make the trade that you risk the bigger tubes to be like shit in terms of like circularity, and the other one, or the pressure pipes, and usually you lose in both scenarios, so that is like a lose-lose. So for this I have brazed a copper T-joint, or not one but four, for the 4 guas, or a 2 fuck me, so the 2 pressure sensors that has like 4 different pins, but they need 4 different sections. And yeah, I have done that yesterday. We'll show it probably in the tomorrow's video when I will assemble it. And also I thought about it. I have had the check valve, the one-way check valve, in the opposite direction as as it should have been. So basically the burner's input was like the other pressure sensor was putting in the air, but it couldn't escape, so that is why it wasn't lighting up, because the air was coming in, but from the other side the air was going in as well, so the SO2 couldn't go away, so it kept the SO2 on the fire, and it's extinguished itself. So yeah, enough for talkie. We'll talk about this and what I have been doing today. I'll show it. So yeah, here's the mess that I have been doing. So yeah, you have been seeing these, and I've been cleaning up the parts, these. This is the last one, I believe. There are like 4 wheels, or 4 like gears, if you want to be very precise. And there are like the motor housing, then the clamps for these. And you have seen this probably, but if you don't know, I'm just going to quickly explain it. So basically, we have the motor here that spins, if I find it, this one. This one has the like a star, or like this I don't know what, spliny thing in there, that will connect to, if I might find it, I don't know where it is, where did I put it? I put it here. So yeah, this spline goes into this goes into that. This is necessary because if you think about it, this is a fixed down house, and what you want is to turn this with the motor basically, but and turn this as well, but because this needs to move up and down, this needs like a thread, but that means either this or this has to move. That way I designed this so this moves inside this spline, that it can slide in and out. Of course, I don't just run it dry, I use like Vaseline for it to be able to like have a smoother operation, because if you don't know about it, there's like a behavior in material science that it is called stick slip, which means that so when you have things that are on things, you have like surface area imperfections, like little mountains and dips, like valleys. They tend to catch into each other, so this has that as well. If you have the same material, that's even more like worse in terms of that. With this is worse. So with this, if I put this in and it rests, then it will have a bigger resistance than when it is like moving. It is like the static friction is always more than the dynamic friction, and because of that, when there is static friction but there is force, this thread pulls it in, it starts to stick until a point, but as the tension increases, as the spindle is turned, that there is more force that it pulls. With enough force, this will start to move with like basically it overpowers the static friction, and then it jumps, but it doesn't like go smoothly, but it jumps one. So it sticks, then it slips, then it sticks, then it slips again, and this is like binary, like jagged motion, which is not good. So this is why you need like in like sliding surfaces, you always need a form of grease or some sort of like inner lubricant that will work. And I don't want oil or some shit flowing all over the place, so I use Vaseline for that. So that explained. So yeah, this is turned. This turns this big gear, which reduces it's 3.9 times in totals between the four gears. So this spins this spins. This has the same shaft as this, basically this one, with this with this rectangular thing that fits in the middle. So this basically has like, they basically have the same angular speed, and this little one spins this, which is the pod gear, which between this and this there is an increase in torque 3.9 times and a decrease in speed 3.9 times, because this needs to move like 10 millimeters forward and backwards. That basically the total motion. This only can turn 1/4. This needs 3 turns. This needs to turn like less than a turn, which is 3/4, which is like 3.9 times or so, or something like that in total relation or whatever. Motor spins this spins this goes forward and backwards. With that, this spins this spins with this spins this, and this is basically connected to the pot meter. The pot meter is on here, and basically this, and this gives us the value, the feedback that we want, and we can adjust it with proportionally, or like have like a stable value that we can control. So yeah, on the other fact, or the other things that I have been doing today, which is like, this is going to be a long ass video, but this maybe I'm going to show you. So this is it. This is very poor in terms of like I probably should have recorded this with OBS, but I'm lazy as fuck. Just going to upload this like this. So this is a T-joint that I have been talking about. This connects to the leveling of line that I have been working on the last few days, I think too. And this will suck the water, the lime water from the reservoir through the line, through the equation out, the level line, whatever. This is basically the suction line of the pump, the water pump, that is the spray pump that pushes the water to the spray head. Then the water, this is basically the water level, imaginary water level. If the water level is up, this float will move up. Float will move up. Oopsie doopsie. Burp, burp, burp. Right. So let's say like this. Till a certain point, then it hits the side on here. This line is connected to a pipe that goes out. So we want that to be not interfering with this, as well as like we have limited space, so it can't have a long lever. In reality, this doesn't represent it very well, but because this has a hole and this has a hole as well, and this has a hole as well, this with this hole is connected through a wire, like a 1mm wire, which I don't have here, whatever. So it is going to be connected here, and it can rotate around this and this. It has like a fixed distance. This, on the other hand, is not fixed to this, but is fixed or is like pinned to the float and this buoyant thingy, and or buoy thingy, and it is fixed here or pinned here, and basically it can rotate around it. As this is fixed, when the water level increases or decreases, this is moving up or down. When it is increasing, it is moving up, and with that this rotates around here. If it rotates around there, this will also like go down. This side will also go down, if you can imagine. This T-joint has like this flow plug. This has like a O-ring on it, which will seal the whole thing down. And when it is pulled out, there is like a increasing diameter here. This is like conical thingy. This can allow the water to go inside. Maybe we'll add more of a increase in diameter, so it will be more aggressive. Probably will do that. But other than that, when it is going up, it goes down. It allows the water to go inside and suck through this line. This line has more resistance. But when this goes down, you can imagine that this fixed line is not going to move. As it goes down, it will start to rotate in and push this basically inside. That, and as well as like this sucks, this will suck it up and keep this nice and sealed, and it will only suck the water from there. And with this, it will basically be able to like limit itself and not be able to like suck air as well, because now when I don't have this, it sucks the water from this level, and it will suck like the air as well as like water from here. But that is not good enough, because the cavity will wear the pump out in a very short amount of time if we still run air through it. So we want to basically cut off any air that can be going to the system. So this is what I have been working today with the modeling and all that shit, measuring, and yeah. So that's it for today. Thanks for watching. Do the hard work, especially when you don't feel like it. Mwah.